So let's say a question asks you to graph this function. What type of a function do we have here? How would you classify this function? What degree? Yes. So we know for transformations, right? In order to graph something, if you want to do it through transformations, you have to be in this form. Doesn't matter what the function is, or if you're going to use point mapping rule, this is the format your equation should be in. Are we in the right format? We're not. So a quartic polynomial, okay, the right format for a quartic polynomial would be something like this. Y equals 3, and then maybe a k value, maybe a d value, and a c value, like that. So you would have to have the power 4 on the outside of the function. That's the right format. And this is much easier to graph. Currently, though, as we see it, it's not in the right format. What does that tell us? It means we cannot graph this using point mapping rule, our traditional means. So the way to graph this function, if it's even graphable, is by factoring it like we do with quadratics. In order to factor a higher degree polynomial, even degree 2 polynomial or higher, step number 1 is to always move everything to the same side of the equation. Now we're going to try and factor this. It's a little bit more difficult than it looks. To factor this, we're going to use something called the remainder theorem. Now, what does the remainder theorem tell us? Let's say you have some function f of x. So the remainder theorem says f of x is divisible by a divisor, and the divisor is going to be in this form. It's going to be linear. X minus a if f of a equals 0. This is a combination of remainder theorem and factor theorem. Here's a quick example. Let's say you have function x squared plus 3 equals 0. The possible a values are always factors of this number. So the possible a value here is going to be plus minus 1. It's 1 and 3, but we include the plus minus as well. So those are the possible a values. So now we're dividing x squared plus 3, or start with the first one, by x plus 1. So here the a value right now is -1. All you do is you're going to plug the a value into the function. That's what this means. F of a means you plug that a value into the function and see what number you get. So if when I plug -1, we get f of -1 is going to be -1 squared 1 plus 3, 4. F of +1 is also 4. F of -3 would be 9 plus 3, 12. F of +3 would be the exact same thing, 12. So notice how none of these gave us a 0. What that means is that this function here, you cannot factor this. To be able to factor it, you must get a 0 from one of the a values. So how do we graph this? Oh, when you can't factor it, usually means there's no x-intercept, usually. Sometimes it's like with the quadratic formula, remember that? It's not factorable, but just because it's not factorable doesn't mean it doesn't have x-intercepts. But this function x squared plus 3 looks like this. This one doesn't have x-intercepts for sure. So that is the idea behind graphing higher degree polynomials. We factor it, we use the properties of the x-intercept, properties of the y-intercept, and then graph it rather than using the point mapping rule. All right, let's look at this again now. So what are the possible a values? Again, look at your constant. What are the possible a values in this question? Exactly. So we're going to do f of minus 1. So what's that? 1 plus 5 plus 1, 6. F of positive 1, it's still the exact same thing. It's not 6, it's 7, sorry. 5 plus 1, 7, 7. Is this function factorable? For it to, yeah, exactly, it's not. For it to be factorable, one of these, at least one of these has to be a 0, which it's not. So as is, this function is not factorable. What that means for us is that we can't really graph this precisely anyways. What we could do is, we know this is a degree 4 polynomial. Degree 4 polynomial is like a quadratic. It starts here, it ends there. We know the y-intercept is 1. So now we can just basically only extrapolate what it possibly could look like. What you could do is actually, if you want to be a little bit more technical, you see these, what do we call these things? Turning points. What do they have in common? What's special about a turning point? What's the slope of the tangent line at a turning point? 0. So what we can do is well, let's find out where the turning points are. So what we're going to do is we're going to find the first derivative. So here, y prime, the first derivative function, you know how to do this. It's going to be 4x cubed plus 10x. Do you agree? So what you do is you set this equal to 0. Basically tells you for at which x value are the slope of the tangent line 0. In other words, this equation, once you solve for it, will actually tell you where the turning points are. So to solve this factor, so 2x you can pull out, you're left with 2x squared plus 5 equals 0. So this means there's a turning point at 0, and then a turning point at, no, the other one is invalid. You can't have the square root of a negative number. So this method only helped us find that, well, we know for a fact that there is a turning point at x equals 0, which is where the y-intercept is, in fact. So we know this y-intercept, there's a turning point, so we can fix this graph a little bit. And there we go. That's an example. So what that means, though, is that there's only one turning point for this curve, and it's right here. It's going to go forever. It's going to go forever. And on this side as well, we can only have one turning point, so it has to come from a very specific direction. Like that. And you have one turning point there. And there you go. That's a possible sketch for this. Did that make sense? This one was harder because we could not find any factors. So we could not factor, so graphing it is going to be more difficult. Let's try this next one. So the possible a values here are what? Okay, let's test it. I don't think one's gonna work. 1 plus 3, no, one's not gonna work. What about negative 1? Negative 1 plus 2 plus 3. That doesn't work either. Let's try plus 3. So 27 minus 6 plus 3. That doesn't work either. What about minus 3? Minus 27 plus 6 plus 3. That doesn't work either. So neither of these are, unless I'm missing something. Yeah, no. None of it worked. So let's go back here. So what can we do when none of it works? When you can't factor it, what can we do? We know a cubic function starts in this quadrant, ends in this quadrant. We know the y-intercept is 3. What we can check is, well, are there any turning points? Because A cubic function can have up to two turning we need to see where the turning point is, right? Cubic function can have two turning points. How do we find the turning point? You set the first derivative equal to 0. What would be y prime here? Yeah, so set that equal to 0. So that means 3x squared is 2. X is going to be the square root of 2 over 3, right? So what's that? So it's like 0.82. And what you can do is you can put this point back in here as x to find the y values of the turning point. So we know there's a turning point at negative 0.82, and we know there's a turning point at positive 0.82. So I'm plugging the values in there. So answer squared cubed minus 2 times the answer plus 3. So I get here it's 1 point, so the y value here is 1.91. And on the other side, it's 4. Will this have x-intercepts? Yes or no? Look at where we are starting. Look at where we're ending up. Are there any x-intercepts? Yes, there are. There must be because it has to cross the x-axis. We have to go all the way there. There's no way to get there without crossing it at least once. But we don't know where it is because we were unable to factor it. So at 0.82 and 4, right here, there's a turning point. And right here, there's a turning point. Now look at how I connect these. So the x-intercept has to be on this side. It would not make sense for the x-intercept to be here and then it somehow curves back in here. So let's start here. So x-intercept is somewhere here. We don't know where it is. And then it's going to go through the y-intercept. And then it's going to go through this turning point. And then boom, there you go. So that's as precise as it gets for graphing a cubic function by hand. This one was also a little bit more difficult. Well, we're always going to do this, by the way. Like, we're always going to make the graph more precise by finding where the turning points are. But on top of this, what we will do is we will factor it, put in all the x-intercepts, put in all the y-intercepts. We'll just do a quick recap on how to graph a function that is factored. Okay, what is the degree of this polynomial? 4 is correct. Positive or negative? Positive. So you know a degree 4 polynomial is just like degree 2 polynomial. It's going to start in Q2, end in Q1. So we're going to start here. We're going to end there. What do we know? Now it's in a factored form. In a factored form, you will be given the x-intercepts. You'll always be given the zeros. But again, you're going to compare it with like x minus a, okay? What are the zeros for this function? Yeah, 0, 2, and negative 5. So right there, let me use a different color. Right there, right there, right there. Um, Here's a pro tip. If your function is in factored form, unless the question asks you to do not bother with turning points. Because right now we're gonna have to use the product rule twice. It can become a bit convoluted. We're only gonna take the first derivative if it's in the standard form, okay? It becomes much easier. Right now, taking the first derivative is not worth the effort. So what else do we know? Do we know the x-intercept? Sorry, do we know the y-intercept? Is there a way we can find the y-intercept? Right, so f of 0. Well, do we even need to plug it in? What do you think the y-intercept is when we plug x value of 0? It's going to be 0, right? Because you're going to multiply. It doesn't matter what this becomes. This you're going to multiply everything by a 0, so it's going to be 0. So the y-intercept is at the origin. Okay, now let's connect the dots. We start there, we end there. Remember this, okay? This is a degree 4 polynomial. Degree 4 polynomial. It can have up to 3. Doesn't mean it has to have. It can have up to 3 turning points. It's always n minus 1, the number of turning points from the degree. If your degree is n, then the number of turning points is n minus 1, up to maximum. Maximum is n minus 1. There's something special about one of the zeros, this one. What's special about this? It's power 2, okay? We call this a order 2 zero. This is order 1, and sometimes you get order 3 as well. So order 1s, we don't have to worry about it. Order 1 means you just cross. The line just crosses, okay? Here's what I mean. So -5, the line's gonna come and it's just gonna cross it. At 0, it's just gonna come and it's gonna cross it like that. You see? Order 1, it just crosses it. For order 2 zeros, they're always turning points in and of themselves. So here, what's gonna happen is that it has to come back down to this 0. But at this 0, we have a turning point. And there you go. You're done. Easy peasy. All of these are the same. Once you can do one, you can do all of them. So again, here the y-intercept is going to be 0, right? Because the x-intercept is 0. So we know our function is going to go through the origin. Terrible straight line. So I'm going to be a bit quicker here. So look at this. There's a 0 at 0. And the degree of this polynomial, what's the degree of this polynomial? Is it 7? No. Try again. It's not 5. It's 6. All you do is you multiply the x terms. That's all you have to do. 3, 4, 6. So it's a degree 6 polynomial. Again, it's nothing to be scared of. It's the same as degree 2. But now the leading coefficient is negative, right? So it's like a quadratic. Instead of opening like this, it's going to open like this. Q3, Q4. So we open down here. We end down here. So one of the zeros is at 0. The other 0 is at -2. And the other zeros are at +5 and -5. You agree? I don't think this is very hard. So -2 is here, -5 is here, and then +5 is there. So all of these are order 1 zeros. That means you're not going to have a turning point at the zeros themselves. But in order to come back there, you must turn. So let's see how this makes sense. So you go up there, come down here. I missed 1 0. Which one did I miss? I missed the 2. Go up here, come down to -2, come down to 0, come down to +5, and there you go. It looks like an M. And we could technically find these. Again, they are turning points. The way to find them is you set the first derivative equal to 0, but because it's not in a standard form, we're not going to bother with this because that would force us to use the product rule twice, and it's not very fun. If you want to, though, I'll show you. So you know what? We're feeling brave. Let's find the first derivative of this. So here's what the product rule says. If your y is in this form, f times g, your y prime is f prime g plus f g prime. This is the product rule from calculus. What are we using this to find the first derivative? To find the turning point. So here what I'm going to do is I'm going to pretend like this is f, because we have three functions, that's why it's a little bit more difficult. We're going to pretend like this is g. So now f prime, we're going to have to use the product rule in f again, because it's made up of two functions. Actually, we can be smart. I'm going to be smarter here. The rule's still the same. What I'm going to do is, because there's no power in here, I'm going to multiply in here. I'm allowed to do this. So we're still at f. That's going to be negative 6x4 plus, I guess minus, negative 12x3. Like that. So now that's our y. This is f. This is g. F prime is negative 24x3 minus 36x squared. This is the derivative of just f. G prime is much easier, it's 2x. Now let's set everything inside of this equation. So therefore the derivative of this entire thing is f prime negative 24x3 minus 36x squared times g g as it is, not the derivative g as it is. X squared minus 25 plus f as it is, negative 6x4 minus 12x cubed times g prime times 2x. And there you go. That's your first derivative. What we do from here is we set this equal to 0 and try and solve for x. I don't know how to begin. I do know how to begin. You open the brackets. You open all the brackets, you're going to get a degree 5 polynomial, which is not going to be the easiest to graph. And there you go. Okay, so turning points, finding the turning points, if it's not in the standard form, is not easy at all. But that's how you do it. If the question really forced you to, you'd open this bracket and see if you can factor that using factor theorem. It's a degree 5 polynomial. We're not going to waste time there. Which one looks good? They all look okay. Okay, what type of a function do we have? Correct. How do we graph this? Well, we're going to factor it. Okay? If possible, we're going to factor it. Here's a pro tip about factoring stuff, especially quadratics, okay? If you can clean up your function in the beginning, it'll make your life much, much easier. By clean up, I mean sometimes thing cancels out. Sometimes you can pull out stuff, right? Can we pull out anything here? We can pull out an x, right? We call that the GCF, the greatest common factor. You always want to pull out the GCF. We can't pull out a 3. Nothing really goes into 9, so we're kind of stuck. We can't pull out a number, but we can definitely pull out an X. So what was the point of doing this? The point of doing this was before we had a quartic function, now we have a cubic function. It's a little bit easier, one less step, one less long divisions, less synthetic division to do. All right, what's the next step? Our goal is to factor this, the inside bit. We need to see the x-intercepts. Yes. Yeah. So there's going to be so many here now. This is going to be painful. Plus minus 1, plus minus 2, plus minus 4, plus minus 8, plus minus 16, plus minus 32. Right? So I'm going to cheat because I don't think one's going to work. We're not going to put everything in there. Minus 42x squared plus 64x minus 32. Okay, so I did some magic maths, and turns out in this function, if you plug f of positive 2, let's prove this. So 9 times 8 minus 42 times 4 plus 64 times 2 minus 32. 2 is definitely works. So you would get a 0. What does that mean? We have a factor. Yes, right? Did that make sense or no? So that means x minus 2. Remember, it's always x minus k or x minus a. X minus 2 is a factor. And then what you do is you have to do long division or synthetic division. I'm going to show you how to do synthetic division again. It's way quicker than doing long division. Always compare this with this, right? Your a value should be on the outside. So our a value here is going to be a 2, not minus 2. It's going to be whatever you plugged in here. But when we factor it, when we write down the equation, we write it in this form. So there's your 2 there. And then we're going to write down all the coefficients now in order of reducing degrees. And if any degree term is missing, we would put it as a 0, like that. So synthetic division, we always add. The first number always comes down as it is. And then we multiply this with your divisor. So 9 times 2 is 18, goes here. That's negative 24. We multiply negative 24 with this negative 48. Add them up, you get positive 16. 16 times 2, positive 32. And the remainder is 0. We knew this though, right? This worked out. What does that mean? It means you should get a 0 here. If you don't get a 0 there, that means something went wrong. What's the quotient? Any idea on what the quotient is? I'll give you a hint, it's right there. We're dividing x cubed by x, right? We're dividing this cubic function by x minus 2, a linear function. So your quotient, yeah, exactly. Your quotient is going to be 9x squared minus 24x plus 16. Cool? And then what we're going to do is we're going to factor that further if it's possible. We're going to man this. 9x, I'll help you with this. I don't know if the numbers are possible. So this is our quadratic. Two numbers that multiply to 144. Oh, it's 12 and 12. And add to negative 24. It has to be negative 12, negative 12. There we go. This one's manageable. So let's split this. You know how to factor a quadratic. At this level, we know how to do this. Not going to waste too much time here. And if you're not sure about this, we have tons of videos on the exact same thing. Like that. Did that make sense? 3x, 9x squared, 12x. It makes perfect sense. So 3x minus 4 squared equals 0. That means this is your x-intercept, but keep in mind now this has an order 2. And the other x-intercepts were what? 0 from here, right? 0. And then 2 from here. So we have 3 x-intercepts. 0, 2, and 4 over 3. But 4 over 3, it has an order of 2. So let's just make a quick sketch here. So the original function, I'm looking at the original function. It's a quartic, degree 4. It's positive. Starts here, ends there. The x-intercept is 0, means the y-intercept is automatically 0. It's at 2. And then there is a order 2 at 4 over 3, which is like 1.33333. Here we have a turning point. So now let's connect the dots. It's going to come through here. I'm going to go through this turning point and I'm going to cross this back out. And you're done. Because is this making sense so far? Because they gave us the function in the standard form, what we could do is we could try and decipher what their turning points could be as well. It's not that difficult if it's in standard form. Okay, so what are we doing? We're trying to take the derivative of this. You're still getting a cubic function, so I don't know how difficult or how useful this is going to be. So that's your first derivative. If you want to find the turning points, you would do the same thing we just did with this. You'll factor things out, obviously, if possible. You can pull out a 4, and then you'll get a -8 here. You'll look for the a values of that. And then you'll plug it in, see which one works, which one does not. But that's a question in and of itself, right? But that's how you'd find the first derivative. We're not going to do it because it's the same process. Let's talk about transformations of polynomials. Remember, for transformations, we're going to be using the point mapping rule. So the polynomials, for anything, this is the transformation rubric. But the special thing about n is the degree now. The special thing about polynomials, though, is that you can pull the a value out. Check this out. So let's say you have y is equals to 4 times 2 x minus 3 squared plus 8. So currently, you know how to do this. A is 4, k is 2, d is 3, c is 8. What does the 2 do? What does the k value of 2 do to this in terms of transformations? No, it's not. K is the opposite. It's a horizontal compression, right? A would be in fact, I'm gonna remove this A just to make things even more clear here. So just say the A value is 1. So currently this K of 2, it's a horizontal compression by a factor of, I don't know, the nomenclature. Some people say 1 over 2, some people say 2. I'm gonna say this. Horizontal compression by a factor of 2. Compression means it's shrinking. Or you could say a horizontal stretch. Okay, listen to this. A horizontal stretch by a factor of 1 over 2. I would classify in that fashion. They're both okay. Now, here's the point I was trying to make, is that for polynomials, because you know the power, you can rewrite this as this. Y equals 1 on the outside is untouched. All I'm going to do is I'm going to pull out this 2. I'm not going to touch anything else. I'm just going to pull this 2 out. To pull this 2 out, you have to take the power. So look at this. When I pull the 2 outside of this bracket, it becomes 2 squared 4. Now your A value is 4, your K value is whatever, 1, D value is 3, C value is 8. So here's the point I was trying to make. For a quadratic function, power 2 function, horizontal compression by a factor of 2. What does horizontal compression even mean? Compression means it's shrinking inwards. So let's say this is the parent function. A horizontal compression of 2 means it shrinks. All the x values shrink, y values stay the same. So it becomes elongated. Therefore, horizontal compression by a factor of 2 is the exact same transformation as a vertical stretch by a factor of 4. You see that? All we did was we pulled this 2 out. So you can describe this transformation as either HC by 2 or VS by 4. In terms of transformations, they do the exact same thing to the curve. Cool? And this obviously applies to any polynomials, like you can always pull it out, and the factor is always going to increase by the power. Like for example, if you have 3x minus 4 to the power of 3, right? Right now it's a horizontal compression by a factor of 3. What is this a vertical stretch by? What's the factor? If you pull the 3 out, to pull this 3 out, all you have to do is take the power. Look at this. AB to the power of 3 means A cubed, B cubed. Same idea here. To pull this out of the power, just do 3 cubed. So what is horizontal compression by a factor of 3 equivalent to? Perfect. So these two are the same transformations for a cubic function. Let's do a quick example just to hammer this point home. Okay, so now we have a quartic function. I think this is very, very simple. We can do this in less than 2 minutes. A is 2, K is 3, D is 4, C is 5. Any questions so far? I think you're good with this, right? If a question gives you a transformation in the proper format as it is, we're obviously going to use the point mapping rule. There's no point trying to open this, trying to find factors and stuff like that. There's no point doing any of that. We're going to use the point mapping rule. What does the point mapping rule say? XY becomes X over K plus D, AY plus C. So in this case, this becomes X over 3 plus 4, then AY would be 2y plus 5. And now your x and y values for quartic, that's your parent function. Remember, the first table is always with the untransformed quartic function. Give me some numbers for the quartic parent function. So when x is 0, what's y? 0. When x is 1, what's y? That's easy, right? When x is negative 1, what's y? 1. When x is 2, y is 16. When x is negative 2, y is also 16. And there we go. Now we're just gonna plug it in there. How hard is this? So this becomes 4, 5, 1/3, 4.33, 7, 3.66. I'm just plugging things in. 4.66, 3.33, 32 plus 5, 37, 37. So all I did here was I plugged this in there, and then repeat. Use a calculator. Some of these numbers might be off by a decimal. So now we just graph it and we're done. So our function, we don't have a whole lot of points to go off of, but 4, 5 is a nice point. 4, 5, right there. And we know that our function starts in this quadrant and ends in this quadrant. 4.337, boom, boom, 4.6637, okay. So we don't know where the turning points are because we're using transformations. And there you go. That is your quartic function. Cool? Just a quick example. Okay, how do we transform? Let's do, let me find a question here. I want to do some radical transformations. I know the answer is somewhere here. Radicals, radicals, radicals. E. Okay, what's the function here? How'd you classify this function? No, that's a root function, right? It's a square root function. It's not that difficult. What's the a value? Yeah, so it's horizontal, sorry, not horizontal. It's a vertical compression by a factor of 4. Is this difficult? Do you think this is difficult to graph this? No, right? So a is negative 0.2. I'm just going to be negative 1 over 4. K is 1. K is not 1. K is 3. D is minus 7. C is 0. So you have x over 3 minus 7, negative 1 over 4y. And we know that this is the root function, which starts at 0, 0, 1, 1, 4, 2, 9, 3. So negative 7, 0, negative 6.66, negative 0.25. You know what I'm doing now, right? 5 point. Some of these numbers might be off, so don't hold me to that. So let's graph this. So we know the parent function goes this way. We know this function, this is called the boundary value, which is basically like the starting point. So the boundary value changed to negative 7, 0. Okay, and then it's going downwards. So when you actually plot the points, it'll look like this. I'm assuming negative 6, negative 7. We start here, 0, negative, so that's the first point, negative 6, 6, that's the second point. This was supposed to be minus, that's the third point. So it's gonna look something like this. Just connect the points, and you're done. Radical transformation, super simple. One and done. What we're gonna do though is we're gonna take it up a notch. I'm gonna give you an exam question right here. Okay, find the inverse. We're looking for y inverse. You remember inverses? What's an inverse? How would you describe an inverse function? as many things you can say. Yeah, perfect. When the x and y values are switched. Graphically, we know that this function is going to look like this. It's a reflection on like this axis, y equals x axis. So it'll probably end up looking like this. I guess we'll see. I cheated a bit because I know quadratic is the inverse of a root function. And it's logical because when you square root a quadratic, you get linear. So anyways, to find the inverse algebraically, here are the steps. Step number one, y becomes x becomes y, okay? And then you're gonna solve for the new y. So x is on the outside now, equals negative 0.253. Now y is on the inside. There we go. How do we solve this? How do we isolate y here? I was gonna make our lives easier here. So let's multiply by -4 on both sides. Okay, now what? We're trying to solve for the y. You square, and then hmm and then you subtract a 7, right? Done. So we know that this quadratic has a y-intercept at -7. It has some vertical stretch, and it's opening up, so it's definitely gonna have 2x intercepts. So it'll look something like this. And our other boy, what was it? It was this guy. We graphed it. It looked like this. So this is your y, and this in blue is your y inverse. Are they both functions? Yes, they are both functions. What if we flip it? Same question. Are they functions? So now we're going to start off with the thingamajig, with the quadratic, and we're going to work our way backwards towards the radical. The inverse of a quadratic is a radical and vice versa. Here's a pro tip, okay? Be in vertex form to do inverses for quadratics. Why? Let's see why. Let's do it the way we've been doing it. Let's just switch x and y's. I don't think it's the end of the world, but let's see. You get something like this. You see that? How do you solve for y there? You can't. I guess you could try and like conjure up something like this, but it's still you're stuck because you're trying to isolate y, and there's always gonna be a y on the other side. You see the issue? If it's not in the vertex form, you're gonna find it very difficult to only have y on one side of the equation. Yeah? So that's why you need to be in vertex form. How do we find the vertex of a quadratic? There's many ways to do it. There's one very quick way. The quickest way to find the vertex of a quadratic. It's this. Your vertex h is minus b over 2a. Minus 5 over 2, negative 2.5. You see how easy that was? And then we're going to plug it back in here to find the k value. Literally plug x as negative 2.5. 5 squared plus 5 times negative 2.5 plus 6. -1/4. So now, in the vertex form, we have this. This is a y. A value, that's the thing about the forms. The A value is the one constant between standard form, vertex form, as well as the factored form. The A value here is 1. It's attached to x squared. So that number will never change. So then it will be, remember, vertex form is x minus h. X minus h squared plus k. So when h is a negative number, double negative becomes a positive. That's why this is a plus. Now let's find the inverse. From here, it's easy. The hardest part was knowing that you need to be in the vertex form, otherwise it's very difficult. Okay, how do we solve for y here? Yeah, and then okay, you square root it, right? Not square, you square root it. What happens when you square root it at this level? What comes outside of the root? Plus minus. And then from here, we subtract 5/2. There you go, and that's your y inverse. That's the inverse function. There's something special about this inverse function. The quadratic is obviously a function, so let's not even worry about it. This is obviously a function. It's a quadratic. Let's try and decipher whether or not this is a function. What do you think? Is this a function? It's not. You'll see that this is made up of what? Two functions. It's made up of -5/2 plus x plus 1/4, yeah? And it's made up of -5/2 minus x plus 1/4. We can graph both of these very easily. This is a vertical shift down. This is a horizontal shift to the left. So think about your parent function. Looks like this. So it went a quarter to the left and it went 2.5 units down. So the top function will look like this. The bottom function, what's the difference between the top and the bottom function? The difference is that the A value is -1, which means it's a reflection on the x-axis. So instead of going up like this, it's going down like this. So this is the negative, this is the positive. But obviously, both of these make up y. Y is a combination of both of these guys. Is this a function? It's not. Why not? Correct. So here's a quick way we could have seen all of this at the very beginning, okay? At the very beginning. And here's the thing. To see, okay, you have y and you have y inverse. Obviously, y is always much easier to graph. Usually, not always, but y is easier to graph than y inverse. So if the question is simply asking you whether or not y inverse is a function, okay, what we do is, this is for inverses. For inverses, we use horizontal line test, not a vertical line test, horizontal line test. Why? Because inverse as x becomes y, y becomes x, the horizontal line test turns into a vertical line test for this guy. So check this out. We do a horizontal line test. It crosses it twice. That means y inverse is not a function. And we could see that from the beginning. As soon as you graph y, do a horizontal line test, and that'll tell you whether or not y inverse is a function. All right, let's call it there for today. See ya.